by Chris Davidson, who is a GSHPA council member and also the director of Genius Energy Lab. Chris has got over 20 years of experience in design of ground source heat pump systems. And I don't know if you want to add anything more to that, Chris.
That's fine. That'll do, Stephen.
Fine.
Kind introduction.
So without wasting any more time, I will now pass you over to Chris. The only thing I would ask, if you have got any questions, rather than raise your hand, we shall wait until the end, but at the bottom of your screens, you'll see a Q&A, a little bubble. If you could ask your questions via that, rather than chat, that would be great. Okay, over to you, Chris.
Thanks, Stephen. I'll just quickly share my screen up and we can make a start. So, well, thank you very much for your time today. This is going to be a little bit more of a scientific one than previous sessions. I'm going to try and keep it popular science, so it's not going to be hardcore equations or anything like that, so please don't worry about that. And it's about electrification of heat and the ultimate efficiency that can be achieved with the electrification options that we have available to us. And as I say, it's going to be a bit of a popular science one, but what I hope is at the end, you get some really interesting insights and a really cool little tool to take away with you that can really allow you to assess whether somebody's perhaps over-promising with what they can deliver with electrification of heat technologies. So without further ado, I'm going to introduce this rather dapper and erudite gentleman, Second Lieutenant Carnot of the French Army. He was a military engineer and scientist and a great physicist. He only actually published one work, which is Reflections on the Motive Power of Fire in 1824, before tragically, and I'm afraid that we are all too familiar today with epidemics, but tragically the epidemic that was rife in France and claimed Carnot's life in the 1800s was cholera. And he unfortunately died of cholera. It was unfortunate, not just as a personal tragedy for Carnot and his family, but also the standard procedure at the time for somebody who died of cholera was to dispose of their belongings by fire. So really tragically, a lot of science was potentially lost in cleaning the Carnot estate. But that having been said, he's recognised as the father of thermodynamics and has left a tremendous legacy, even with that one publication. I'm going to come back to Carnot in just a second, but what I'm going to do first of all, and it's customary in presentations, I guess, to get to further reading at the end. I'm going to deal with further reading at the start, and hopefully you'll see why in just a second. I'm going to quickly talk through the 4 laws of thermodynamics. Now, this is not an explanation of the subject in its entirety. It's just to give you a feel for what these 4 laws say and what they tell us about the nature of the universe. So the first, there's a link there on the presentation to the laws of thermodynamics on Wikipedia. And if you type laws of thermodynamics into the search engine in Wikipedia, you'll get a really good explanation of it if you're interested in doing a little bit of further reading. So first of all, the 0th law of thermodynamics. This defines temperature. And just to give you a feel for how this works, if we imagine we've got 2 bodies, so 2 blocks of metal, whatever you want, block A and block B, and they are in contact and in thermal equilibrium with each other, so they're at the same temperature. So block A is in contact with block B, and then imagine there's a third block, block C, which is in contact with block B. Then that defines the fact that if they are each in thermal equilibrium, then A is in turn in thermal equilibrium with C, which sounds like a really trivial result, but actually allows you to do things like have a thermometer that you can put in one body of water and establish what its temperature is relative to another. So it might seem a little bit basic, but it's actually a very subtle bit of physics that allows a lot of the mathematics that sits behind temperature to be defined. Secondly, the first law, confusingly it starts at the 0th for historical reasons, but the first law is all about the conservation of energy. So in a given system, as they often say in thermodynamics, energy is always conserved. So that means that energy within that system cannot be created or destroyed. It can only be converted into different types of energy. So for example, mechanical energy, I can turn into heat by rubbing my hands together, Miyagi-Do style. Second law of thermodynamics is about entropy, or disorder in lay terms. So the disorder of any system must increase with any physical process, or the disorder of the universe in total must increase whenever anything happens. And the classic is the match that I've chosen for the picture there. So if you strike a match, it will burn, and the disorder of the universe will increase. And that's a very likely to happen thing. It's very unlikely for that to spontaneously unhappen. And that gives you a clue as to some of the weird things that are associated with entropy and the increase in disorder. They may be weird or counterintuitive, but it doesn't mean to say they don't actually happen. And that's one of the key points of physics, is that it might seem a little bit odd, but that's actually how the universe works. And so because entropy must increase, for example, it's postulated that that's the reason why you can't remember the future, because and that's because entropy gives a direction to time. The third law of thermodynamics defines absolute zero temperature, which is minus 273.15 degrees Celsius. And that's important. I'll come back to it in a second. We measure that as Kelvin temperature, and I'll come back to it in a sec. So as I say, this is not meant to be an exhaustive lecture on thermodynamics. It's just to give you a feel for what's going on with it. And by all means, have a look at some articles or potentially books to learn a bit more. So going back to Carnot and his theorem, it's a consequence of the second law of thermodynamics predominantly. And I'm just going to read it out. I don't normally read slides out, but I'm going to do it in this instance. So Carnot's principle is the efficiency of a quasi-static or reversible Carnot cycle depends only on the temperatures of the two reservoirs and is the same whatever the working substance. And a Carnot engine operated in this way is the most efficient possible heat engine using these two temperatures. Now I'll just highlight a few points in that. So firstly, it depends only on the temperatures of the two heat reservoirs. So the efficiency of an engine, of a turbine like this chap here is putting together, is dependent only on the temperature difference between the hot side and the cold side. It's not dependent, or the theoretical efficiency, I should say, is dependent on nothing else. The second point to bring out is this is the most efficient possible heat engine. So a heat engine being an engine which uses work and heat to do something. Okay, that's the theoretical maximum it can achieve. And finally, and this is really relevant to this discussion we'll have in a little while, it is the same whatever the working substance. So whatever we are transferring heat to and from, it is absolutely the same. So if that's true for heat engines, what's all this got to do with heat pumps? Well, actually, the process of understanding a heat engine, like a steam engine or a steam turbine, using Carnot's principle can be applied to heat pumps as well. And that's what we'll go and do now. So the key point to get away from this is there is absolutely a maximum efficiency that is theoretically possible from a heat pump. And you cannot go beyond that. It's no matter what you do, you cannot go beyond that. And that's a key point that comes out of Carnot's theorem. And that's defined by the temperature of the hot side divided by the temperature of the hot side minus the temperature of the cold side. And those temperatures are in Kelvin. Okay, so if you want to get to degrees Kelvin, it's degrees Celsius plus 273.15, that magical minus 273.15 absolute zero temperature. Okay, put another way, to give you an idea about Kelvin temperature, we in our world live at around 300 Kelvin. That's our normal habitat. Now that simple equation of temperature divided by temperature minus temperature gives us the absolute maximum efficiency that a heat pump can achieve in heating mode. There's an analogous equation for cooling, but I'm not going to complicate things by getting into that now. Second key point is it is absolutely impossible to achieve that maximum efficiency because you'd have to get rid of all friction and all losses from your system. And by the other laws of thermodynamics, getting rid of friction is impossible, or entropy wouldn't increase, for example. So if that's a theoretical construct, why am I wasting your time with it? Well, actually, it can be very useful. It can be very useful if you start to look at it in terms of percentages. So let's look at some of these percentages. So I'm looking at three technologies that are available for the electrification of heat: direct electric, air source, and ground source. And the direct electric is trivial. Carnot's principles don't really affect it. It's got an efficiency of about 100%. So if you buy an electron to heat your 3-bar electric fire, you'll get exactly that amount of heat out of the fire. But it's more interesting when it comes to heat pumps. So source, let's look at a source of 0 on both an air and a ground source. So the air is at 0 and the water in the ground source is at 0. Let's look at a load temperature of 45 degrees for both. So it's the same on both sides. The Carnot efficiency of that, if you plug it into the equation above, remembering to convert to degrees Kelvin, is 7.1. So back to the point earlier, the Carnot efficiency is only dependent on the temperatures of the reservoir and not the medium itself. Okay. Now I went to Wikipedia and I typed in efficiency of heat pumps, and for a 0 degree source and a 45 degree load, it gave me these typical efficiencies. And I've just put the COP of 1 for the direct electric. So this is how much heat am I getting delivered into my building per kilowatt hour of electricity I buy. With direct electric, as I said earlier, it's 1. With air source, the typical number published in Wikipedia is 2.8. And again, on ground source, it's 3.8. Now, the reason I just went to Wikipedia rather than going to manufacturer's data is because it does vary by manufacturer. It does vary by size of heat pump, for example. A smaller heat pump will tend to be less efficient than a larger heat pump. So there are variances in this. So I wanted just the number that is out there and accepted and peer reviewed. So back to our percentages, we can simply divide our 2.8 and our 3.8 by 7.1, and we get the percentage of the Carnot efficiency that we are typically achieving with our heat pumps. 39.4 with air source and 53.5 with ground source. Okay, I'll come back to the differences in just a second. Just one point to make. These are rating point coefficients of performance, COPs. So at that particular temperature regime, this is what you're going to get out of your heat pump. This is absolutely not a seasonal COP or an average across the seasons. And I like to make that point because this rating point, if you think about it, is actually quite negative towards ground source, because we can control that loop temperature. And 0 degrees, as it happens, is the minimum we tend to work to in our ground loop, whereas air is going to get colder than that. So when you start to translate these rating point COPs into annual seasonal coefficients of performance, you tend to see quite a significant increase in the ground source. You will get an increase in the air source, but maybe less so. So I'm just not going to talk about that in too much detail today, because I think, you know, it's quite a lot to digest anyway. So let's just talk briefly about carbon. If we apply the SAP 10.1 carbon factors that are out there, hopefully going to be accepted fairly soon, then you just divide those carbon factors by your COP, and you can see that the Carnot numbers are very, very low, but the typicals are a bit higher. They're still an awful lot better than direct electric, particularly the ground source side of things, but they are not at the theoretical maximum. So I just mentioned that because it's got these COPs have got a really concrete impact on carbon outputs, and that impacts planning, it impacts everything else that goes along, and indeed climate change. So I always like to mention these numbers, even though it's a slight diversion for this discussion. So why is there a difference between ground and air source? Well, it comes down to the stuff other than the temperature that these heat pumps have to deal with. And the first thing we have to talk about is the specific heat capacity of air and water. Now, specific heat capacity is how much energy I've got in a given volume of a substance for a given degree in temperature, for a given temperature difference. So if I've got a cubic meter of water and a cubic meter of air, they will have a significantly different amount of energy at a given temperature in them. And just to put a quantum on that, the specific heat capacity by volume of air is 0.001297. And the specific heat capacity by volume of water is 4.1796. So to get a crude idea on how more effective water is as an energy transfer, heat transfer medium, if you divide one by the other, you get a number which is 3,222 times more effective that water is at transferring heat by volume than air. So what that physically means is you've got to move an awful lot more air around than water for the same amount of energy going through your heat pump. So that has an effect on the real world efficiencies that are our D-rating, if you like, from our Carnot efficiency. The second thing it's worth mentioning is that fans are effectively less efficient than water pumps, and that's because air is squidgy, whereas water is an incompressible fluid. So it tends to mean you've got a lot more friction going on in an air system than you will do in a water system. Another point to make is, I touched on it earlier, is we can control the minimum temperature that's coming into our heat pump from the ground by putting in more or less ground loop. So the more ground loop we put in the ground, the more moderate that return temperature will become. So in heating mode, the higher that return temperature will come. And the standard under the microgeneration certification scheme regulations is that that's 0 at year 20. So we are controlling that. The heat pump should never see water colder than 0 coming into it at the end of that design life. Okay. Air source, we can't really control the air temperature. It will get colder than 0 as well. Another point to make on air is that, unfortunately, for much of the heating season, particularly in the UK, our air is humid, it's damp, and that means that as you cool that air down to take the heat out of it, you'll get frost building up on the coils of the heat pump. And what that means is the thing needs to go into a defrost cycle. And that defrost cycle always means some energy has to be used to get rid of that ice. Doesn't matter how clever you are with the defrost cycle, some energy has to be used to do it. So your COP goes down. And then finally, a bit more subtle, this one. If you've got an air source heat pump cooling in the summer and heating in the winter, then there's no heat recovery between winter and summer. Whereas if we use the ground, given the right geological conditions, we can actually store a significant amount of that energy in the ground in the summer and get it back in the winter, which improves the efficiency of both the cooling cycle and the heating cycle. And that can be one of the biggest advantages that ground source has. So I very often say, if you've got cooling involved, you really want to be considering ground source because it's such a good way of recovering that energy interseasonally. So the final thing I want to give you is a bit of a toolbox, if you like. We all get people selling us things that they're maybe over-promising and they don't mind under delivery. That happens. That's just the way the world. Sales is like that. So what I'm going to do is give you a little bit of a toolkit on how to rumble a snake oil salesperson. So let's say he or she comes along to you and says, our heat pumps have got a COP of 6. Well, first of all, you can see that that's a completely meaningless statement because it completely depends on the conditions on the two reservoirs, the two heat reservoirs. How hot is my source and how hot is my load? I've got to know that. So first thing to do is ask them also, what's the design condition you're quoting that at? And he or she comes back and says 0.45. Okay, super. So how do we tell if that's a reasonable argument or a reasonable performance or not? Well, what I did was build myself a little spreadsheet. And all I've done here, and you can replicate this dead easy, or you want to email me, I'll email it to you. You put in your source entering temperature, so 0, as we did before, and our source leaving temperature. So there's a temperature difference across the heat exchanger and the heat pump as the heat pump sucks heat out of that water, okay, or air. That then gives us an average source temperature, which we convert to Kelvin. Okay. I've not got the 0.15 in here, obviously. We then do the same on the load side. We've got an average temperature on the load side, and we can convert that to Kelvin. And we simply do the little equation. You can see it in the bar there. That gives us a 7.1. So I've kept this consistent all the way through 0.40, 0.45, and 7.1 Carnot efficiency. Back to our percentages then. So all we do is calculate that percentage. So we divide the claimed COP by the Carnot efficiency. And in this case, we get 84.5. Now, my reaction My reaction to that will be, really? Are you really achieving 84.5% of the Carnot efficiency? Have you really squeezed that much friction out of your system and losses out of your system? So to give you a ready reckoner for it, so you can assess whether that's a sensible claim or not, if you do the numbers on air source, you're typically at 35 to 45% of the Carnot efficiency. And if you do it in ground source, you're at 55 to 65% of the Carnot efficiency. You do get outlying numbers. You can definitely destroy the efficiency of either a ground or an air source by installing it badly. That might be the ground loop design might be poor, but probably more commonly the distribution system is poorly designed. But that's a typical value that you can achieve. And I'm not saying that if you get to 66, that's not possible. It absolutely is possible. I believe there are new compressor technologies coming along that are pushing up towards the 75, 80% of the Carnot efficiency, but they're not commonly available as domestic heat pumps or industrial heat pumps at the moment. So finally, thank you for listening, and thank you to Second Lieutenant Carnot for the work he did those many years ago. And what I'm going to do is go back and ask Stephen to help me slightly and answer some questions.
Thank you very much for that, Chris. I don't know if it's a good thing or a bad thing, but there are no questions to be asked. So
I've bowled them over.
Bowled everyone over there, Chris. I mean, if anyone does want to ask one, you know, pop one in the Q&A box. We'll just leave it for a second or two.
Yeah, sure.
I've learned a few things there, Chris. So that was, find that person very interesting.
That was a mission. I knew it was a slightly different topic to what we've covered before, but I think it's very useful to know it. It's like if you're a cook, the Larousse Gastronomie, the famous French cookbook, it's the ultimate argument ender. You know, you just look it up and you know, how long you fry a scallop for, it's in there. Thermodynamics is kind of like that when it comes to heat pumps. If you go back to the first principles of Carnot efficiency and hit a claim with it, then you can very quickly see where the snake oil is being sold, and those people who are much more sensible about it.
No, that's wonderful. Again, no questions, Chris. So thank you very much for your time.
My pleasure.
Much appreciated. And if anyone does want to obviously get in touch with Chris or anything like that, if you drop me a line in the first instance at info@gshpa.org.uk. I've got my own email address then. That's fine. Just drop me a message and I'll pass that on to Chris for you. Okay, well, thank you all for attending. We are trying to do more webinars. We do try and aim to do the first Thursday in the month where we can, holidays permitting, etc. But please keep your eye open on our website for any more that are coming up. Thank you very much, everyone.
Thank you.